Welcome all in today's lecture Airborne and Spaceborne SAR systems. Myself Ashish Joshi. I am scientist at Indian Institute of Remote Sensing, Dehradun. So in today's lecture we will learn about the SAR system parameters, which is wavelength, look angle and polarization, and what are the different spaceborne SAR systems and airborne SAR systems. So just we will brief about the SAR concepts. So how the SAR signal is transmitted. Actually, normally the SAR is an active sensor. So there are four components which are very much fundamentals in the transmission of the SAR signal. So first is the frequency or wavelength. At what frequency and wavelength we are transmitting the data. Okay, so because the frequency and wavelength of a signal is actually interact with the targets, and it will return the backscatter depending on the it is how much it is penetrating and how the surface is rough or smooth. So the wavelength and frequency is the most critical parameters in the design of any SAR antenna. Second is what angle, means what is the angle, which is called the look angle. So at which look angle we are transmitting the signal. Okay, means the look angle also very much affect the SAR images. Okay, the first is the wavelength and second is the look angle. At which look angle, as you know that SAR is a side looking system. So in the side looking system, how much is the look angle? It is 10 degree, 30 degree or 40 degree. So depend on various application we have to decide the look angle, because as you know that in the SAR we have many like layover, shadow and foreshortening. So the layover and shadow and foreshortening, it actually varies depend on what is the look angle. So if the look angle is low, so we are having very much higher layover, and if we are having the high look angle, then the layover will be lower, but the foreshortening will be higher. So it depends on our application, means we are actually imaging a flatter area or hilly area, because if the hilly areas we are imaging and we are taking the lower look angle, then we are getting very much higher geometrical distortions in the form of the layover. So and the third parameter is the transmitted power, what power we are transmitting. Okay, because as SAR is an active sensor, so we have to transmit enough power so that the return signal have enough energy so that we can detect a signal. Okay, so it will actually impact on the image quality, how much is the transmitted signal, because if the transmitted signal is not higher, then what will happen, it will affect the image quality. We are not getting a good SAR images. And the fourth component is the polarization, because SAR is an active sensor, so we are having the advantage to transmit any signal in the form of either the horizontal or vertical polarization. So advantage of the polarization is that if we are transmitting in a particular polarization, so that polarized wave interact with the target, and the target may change the polarization or may not change the polarization. So if any polarization change is there, then we can deduce the orientation of the target. So any orientation of the target, if it is a horizontal or vertically aligned, it can be easily actually detected if we are having some dual pole or quad pole SAR antenna. Now what is the effect of the wavelength? So wavelength, actually the backscattering is directly related to the wavelength of the microwave pulse as a function of the terrain object. Radar wavelength should be matched to the size of the surface feature that we wish to discriminate. Object appears bright if it matches the size of the object that matches with the wavelength. Means if the wavelength is low, then we can detect a small target. So because if we want to do the detection of the small targets, so we have to choose the lower wavelength actually. So lower wavelength means we have to use the X band. X band have the lower wavelength. So the small feature discrimination, normally we will use the X band, and as we are going to the higher band like L band, then the penetration capability is increasing. So in this figure you can see how the effect of the penetration is on the different features, like if X band is there, then the backscatter signal will actually scattered from the top of the canopy. But see here you can see that in the C band it is actually backscatter from the middle of the canopy, but in the L band it is penetrating through the forest canopy in the case of the L band. So if you want to do some application like foliage penetration type of thing, then we have to use the which wavelength we are working on. So any SAR system or spaceborne SAR system is designed to a particular application. So if we are having the small target detection, then we have to use the X band, and if you want to have some penetration capabilities, then we have to use the L band. And basically it depends on the which wavelength and what is the application is there. Accordingly we will design our SAR antenna. So the penetration capability is mathematically related to the lambda by pi tan theta. Lambda is the wavelength and the theta is the incident angle. So as the wavelength is increasing, though we have the penetration capability is also increasing. So we can see the different bands are there, and the penetration depth in centimeter you can see in different bands. So you can see as we are going to the higher wavelength, the penetration depth is increasing. Now you can see we are having the different band categories like X band, which is from 3.75 centimeter, C band from 3.75 to 7.5 centimeter, and S band 7.5 to 15 centimeter, L band is 15 to 30, and P band is 30 to 100 centimeter. And it has the different applications, like in the X band we are having the small feature detection type of thing. In C band actually we are using the for the soil and agriculture, and S band is also in that category also. But L band is used for the penetration capability and large area mapping and geological mapping type of thing. And P band is actually used for the higher penetration for the estimation of the forest biomass and other applications. So actually our spaceborne SAR system categories depend on this different category of the bands also. So we are having different SAR systems, and it depends on the which frequency we are using. And in this lecture also I have divided the spaceborne SAR system as a different frequencies. So accordingly, what are the X band SAR systems are there, what are the C band, what are the S band, and what are the L band SAR systems are there. So and the second, the crucial parameter is the look angle. So look angle means how it is the angle between the, so in this figure you can see here is the SAR antenna, and this is the angle which is called the look angle, and it is the angle between the nadir and the slant range. So what is the slant range it is making with the nadir point. So this is called the look angle. So what is the effect of the look angle and on the backscatter of the SAR image? So backscatter decreases as a function of the look angle. So as the look angle increasing, backscatter decreases. And in the SAR image from near to far also you can see that as the look angle is increasing, the backscatter will decrease. So large look angle actually interact more with the vertical features, and the smaller angles have more interaction with the horizontal features. So if you are having any agriculture application like sugarcane study, where you want to study the vertical objects, so you can have to use the larger look angle so that it cover the full length of a particular vertical object. But if your application is like soil moisture study and like that, so you have to use the smaller look angle. And the third important parameter is the polarization, because SAR is an active polarization active sensor, so we can transmit the our electromagnetic wave either in the horizontal or vertical polarization. So the radar antennas can be configured to transmit and receive either in the horizontally or vertically polarized electromagnetic radiation. So we can design a single, dual or quad pole SAR system. So when the radar interacts with the surface and it is scattered from it, the polarization can be modified depending on the properties of the surface. Then this modification actually modification affects the scene in the polarimetric radar imagery, and the type of surface can often be deduced from the image. So if any object is oriented horizontally and vertically, so the polarization alteration will be less or higher, and with the effect of the polarization we can say the object is either horizontally aligned or vertically aligned. And some of the studies, like if we are having the HV type of polarization where the signal is completely depolarized due to the volume scattering of the forest canopy of any other thing, so in that case we can design our sensor like HV configuration where the signal is completely depolarized, means we are sending H polarization, but like forest there will be having the multiple scattering or volume scattering, and it will change the orientation of the signal. So if we are sending the H polarization, then the forest will change to the V polarization. So if we will design like HV type of system, then we can have the study of the forest biomass and how much is the vegetation studies we can do. So the cross polarization like HV are sensitive to vegetation and depolarize the signal. So we can see the how the horizontal polarization is interact with the earth surface and how the vertical polarizations are interacting with the earth surface. So the polarization is playing a very important role. Another important parameter is the SAR resolution. So unlike the optical sensor, we are having a single resolution, like if we are having any Sentinel-2 image, or we are having the Indian sensor we are considering like Carto 2S, in the we are having either 10 meter or like 2.5 meter. So it is single resolution optical images. But in case of the SAR, there is a two resolution in both the direction, which is called the range and azimuth direction. Range is the across track direction and azimuth is the along track direction. So in case of the SAR, we are having basically two type, and the resolution cell is also not square because they are not equal also. So we are having different range resolution and different azimuth resolution. So we can have a rectangular resolution cell, and the range resolution cell, you can say it will have the formulation of C by 2B. C is the speed of light and B is the bandwidth of the signal. So in designing a SAR antenna, we have to design the bandwidth in such a way like to have a particular application to get a particular resolution. Like if C by 2B and we are having the bandwidth of 75 megahertz, then we can get a resolution of 2 meter. And if we are having the 150 megahertz, then we can have 1 meter resolution. So from this table you can see that the bandwidth and the resolution are inversely proportional. So higher the bandwidth, then the smaller will be the value of this rho r, which is a range resolution, or we can say we are having a high resolution because the number is small, so we can detect a very small object also, or we can say very high resolution image we can get. So if you want to have a smaller object detection, then we have to use the higher bandwidth, and the higher bandwidth is actually available in the X band. So we will use the X band for the small feature detection. Now this range resolution is mainly depend on the bandwidth, which is depend on the SAR system parameter. But the azimuth resolution in the case of SAR is L by 2. So this L by 2 is the L is the physical length of the antenna, and by using the synthetic aperture concept, we will get a resolution of L by 2. Means if we are having the 12 meter antenna, then our resolution will be 6 meter in case of the strip map mode. So as you know that we are having different imaging mode. One is called the strip map mode, scan SAR mode, and the spotlight mode. So if strip map mode is mostly default mode in every synthetic aperture radar processing system. So we are having the L by 2 resolution in case of the strip map mode, but it can vary depending on the mode. So in the SAR, it is not single resolution, we are having two, one is called the range and azimuth, and multi resolution also, means we are not getting us from the single SAR antenna single resolution, we are getting a multiple azimuth resolution depending on the mode. So if we are having the strip map mode, we are having the we are having one L/2 resolution, but if we want to get a higher resolution, we can go to the spotlight mode, and if we want more swath and less resolution, then we can go to the scan SAR mode also. So it is the important parameter in case of the SAR. And normally all the space-borne sensor will give this type of data products, means it can provide the raw data product which is called the signal level data. So raw data products is actually the data which is received by any space agency, either it is ISRO, NASA or ESA. So they will initially get the raw data, and they will process the data using different algorithm, like there is a range Doppler algorithm, is Spacken algorithm is there, and we have a chirp scale algorithm. So these are some of the raw data processing algorithms which is used to process the raw data of the SAR, and after processing it is given to the users in the form of the processed product, which is the single look complex product, which is containing the phase information, means in that image we are having the real part also and the imaginary part, and some of the satellite will give the detected product also, means they are not giving the SLC product, and they will give directly amplitude image. So that is called the single look detected product. And normally in the case of SAR, we are having the slant range geometry, all the processing will happen in the slant range. So initially everything processing is done on the slant range geometry, and the products associated with slant range geometry is called the slant range products. Now normally the slant range products have not a square pixel size, that are the rectangular. We are having different pixel spacing in the range direction and azimuth direction. Now if we want to make the product like a ground products, like we are having the square pixel size, so we have to project our slant range data to the ground range to generate a ground range product. Now slant range and the ground range, both products are in the sensor geometry itself, means either it is in the slant range geometry or it is in the ground range geometry. It is not on the geographic coordinate system, means it is not projected on the earth. So we cannot compare this image with other satellite image like hyperspectral images and optical images. So we want to project that images on the earth or geographical coordinate system, so that products are called the geocoded products. So we are having different algorithm like geolocation, geocoding, which is used to actually project our SAR images from the sensor geometry to the earth geometry. So the product is called either the GEC product, earth ellipsoid corrected product, or if we are using the digital elevation model, then it is called the terrain corrected product. So these are the different products, how the processing will happen from the raw data after this RDA, which is called the range Doppler algorithm. We are having different products. So now these are some initial sensor parameter which are dependent or we have to use for the designing of any SAR, spaceborne or airborne SAR system. So earlier in case of the SAR technology, we are having in the difficulty in the development of SAR sensor because of very large spacecraft, powerful launchers, and very high cost are there, and very few spaceborne SAR images are there. So they are very much heavy actually, our SAR antennas and that thing. Now in the recent development of SAR, we are having the large reduction in the size and volume of the power generated electronics and components, size and weights of the antenna which is becoming smaller and lighter. So we are having the less cost to launch the SAR satellite. So earlier cases we are having the lesser SAR satellites, but after the recent advancement in the technology of lighter antennas and that thing, so we are having now more SAR sensors in the space. So earlier we can have the like phase array type of system which are having very much higher weight, like we are having 900 kg weight of the radar set, one satellite. Now with the advancement of like parabolic antennas in the form of the mesh, wire mesh, or it can be inflatable antenna structures, so we can just flood up and the antenna in case of the wire mesh, and the weight of that one is around 3 kg of that antenna. So you can see from the higher weights of the 900 kg, we can now go for the smaller satellites also with the smaller parabolic type of antenna. So that thing is the reduction of the weight and the different electronic components in the SAR systems. So now we will see some of the SAR systems within the different frequencies. So we can see, and our normally the spaceborne SAR system categories is divided into the IX, C, S, and L, in which the maximum GSD we can get from 1 to 3 meter in the X band, C band from 3 to 5, S is from 5 to 8, and L 8 to 10. So this is the resolution we can get, but depend on the modes, like the spotlight mode, we can get a better resolution also in the azimuth direction. So azimuth direction is totally depend on the how is the mode, it is strip map mode or anything. So from that we can get a good resolution, but in the range side we have to have the limit of C by 2b. B means the bandwidth of the signal, how much bandwidth is available in a particular system. So if we are having the X band system, then we are having the high resolution in the case of range resolution. So first we will see the X band SAR systems, and so first we will see like TerraSAR X. So TerraSAR X is a X band radar sensor which was launched on 2007, and it has the different modes like strip map mode is there, spotlight mode is there, and the ScanSAR mode is there. So after that we are having the in the TerraSAR also we are having tandem mission also, which is the twin satellite of that TerraSAR X, which are having the bistatic star also. So normally we are having different resolutions. So already I have told you how the resolution is depends. So we are having the strip map mode 3 meter, ScanSAR 18 meter, and the swath width is varying from the 5 to 100 kilometers. So in case of the SAR system we are not having the single resolution, it is having the different resolution, depends on the mode in case of the azimuth, and the range direction, it depends on the bandwidth of the signal. So different satellite products it will offer, like we are having the SLC image which is having the phase information, which is called the SSC product, or we can have a ground range image which is called the MGD image, or we can have the geocoded, which is the earth projected products, and we can have the enhanced ellipsoid corrected image products also. Now after TerraSAR X there is a launch of Tandem X mission, which is primarily used for the creation of the for the digital elevation measurement, which was launched on the 2010, and the orbit is synchronous only. So it is actually flies in close tandem with that one. So it is in the bistatic and monostatic. Monostatic means the transmission and receiving is done on the same platform, but the bistatic is means we are transmitting the signal from one platform and receiving with the other platform, which is called the bistatic system. So it is like a bistatic mode tandem. So we are transmitting with this satellite and received by second satellite. So receiving can be done in this satellite also and this satellite also. So with this type of thing we can able to create the both type of baseline. So it when you study the interferometric classes, then you have the concept of the baseline. So the x direction baseline is called the across track baseline, and in the along track means azimuth direction, if we are transmitting we are separating the antenna, it is called the along track baseline. So it is a X band system, and it has generated a very good digital elevation model, using the interferometric techniques and using the bistatic mode, tandem X and the TerraSAR X. So this is the TerraSAR X image of 1 meter resolution with the spotlight mode of Toronto. So you can see in this SAR image there are some bright features which is due to the man-made structures, and you can see some of the dark thing which is the actually the surface scattering, like rows. And so this circular structure, you can see this is the flyover, and this here you can see some of the electric poles. These dots are there, some of these things, electric poles type of thing. And this is the one building which is giving, and this is all the urban settlements which is giving the high backscatter in the SAR image. Now another X-band satellite, it is launched by the Italian space agency, which is called the Cosmos SkyMed. So it has launched 4 satellites as a first generation satellite and 2 satellites in the second generation. So it was launched on 2007 to 2010 for the first generation satellites, and 2 satellites in like 2019 and 22. So it is also a sun synchronous orbit. So normally for this SAR antenna and for the civilian application, everything is in the systematic manner. So we will have the sun synchronous orbit for the systematic coverage of the every scene. So here the orbit is synchronous, and the altitude is around 620 kilometer. So it has the 16 days revises, means after 16 days we are getting a one scene, and it has the polarization capabilities of single dual for the first generation satellite, and for the quad for the second generation satellite. Means quad polarimetry means it has the full type of polarimetry, and the incidence angle or look angle, it has the option of 20 degree to 60 degree. So we can image a particular area with a particular incident angle or look angle. So if we want to have the lower look angle, it can be of 20 or 30 degree, or we can go to the higher look angle of 40 to 60 degree if we want to image like hilly terrains and where the requirement is the higher look angles. So it has the different resolutions in the different modes. Like spotlight, it can get a resolution of the 1 meter. Strip map, it is given 3 meter, and the 2 modes in the ScanSAR, which is giving the 30 meter and 100 meter resolutions. So another mission, which is the recent mission only, which is called the SWOT mission, which is surface, water and ocean topography. So it is actually the Ka band, actually it is the Ka band satellite. So it is primarily used for the actually the interferometry. So it is directly giving the surface height actually. So and it has also have the nadir altimeter. So it has the capability to have the surface height of the waters or rivers and the oceans also. So that is the technology. In the same sensor there is the both both the transmitter and receiver, and they can just do the interferometry in the single pass interferometry. So in the single pass interferometry, they can directly measure the what is the surface height of the water bodies, and it is having the resolution of 100 meter, and the swath width it is around 120 kilometer. So normally the principle, it is using the interferometry in case of the surface height, and alternatively it has also the altimeter. So using the altimeter also it will have the range measurement. So altimetry actually use the range information to convert to the height, but if you want to precise measurements of any terrain, so we need the phase information. So that Ka band interferometry, it is used to generate the height using the phase information. Okay, so using the master and slave images with the 2 pairs of the thing, we can generate the same area image, and from the phase difference of the 2 images we can generate the interferogram, and from there we can generate the height values. And the revisit capability is 21 days. So it was launched on 2022, and now the full different products are there, and SWAT products are available for utilization. Another expand satellite is the Kepler space. So Kepler space is the commercial actually, so in that it is launched on the 2018, and it has the constellation of the micro satellites. So it is using the concept of the very much which is called the multi looking on the onboard system also. So they are having the higher bandwidth, and they are doing the multi looking and to generate a very much good quality image and with the reduced speckle. So the image quality is very much good in there, so using the higher bandwidth signal and using the multi looking concept to get a noise free, or we can say lower noise in the images. And so it is having the polarization of VV, and we can have the resolution up to the 0.3 meter resolution, and the strip map mode we are getting around 1.2 meter resolution. Another expand satellite is the ISI satellite. So it was launched on 2018, and the major application is for the the ocean ice studies for different applications, and it has also have a constellation. So it is the expand satellite from 0.25 to 1 meter resolution, and we are having the strip map mode of 3 meter resolution and scan SAR mode of 10 to 15 meter resolution, and with the varying swath width from 5 kilometer in case of the spotlight, and the strip map will have the 30 kilometer, and the scan SAR has the 100 kilometer. It is also a single polarization, either HH or VV polarization we can get from the ISI. So till now in the X band we are seeing 3 satellites. One is called the TerraSAR X, one is the Cosmos SkyMed, and one is the Kepler space and ISI, and one Ka band satellite, which is the interferometer, which is the SWAT, which is not a X band but a Ka band satellite. Now after X band, mostly the civilian application is done in case of the C band system. So mostly you can see our systems are which is the free data is available, which is the C band systems. So C band SAR system is a part of the microwave spectrum that has been extensively used in the past, and which are having the satellite like IIRS-1 is having IIRS-2, RadarSat-1, ReSat-1, 1A, Sentinel-1A, 1B and 1C. It has been used for different environmental, agriculture and forest monitoring, as well as maritime and oceanic research also. So we are having the continuity of different satellite, like ReSat 1A is the will have the continuity of 1B. In the same way, RadarSat 1, 2 is there, different satellites in the continuation. So it has the C-band satellite has started with the launch of the IIRS 1 and 2, and later on we are having the NVSat also. So IIRS was launched on 1991, IIRS 2 on 1995, and after that 2002 NVSat is launched. So NVSat have the instrument which is called the SAR, which is called the Advanced Synthetic Aperture Radar, which have the polarization single and dual and different imaging mode of 30 meter resolution. Okay, and it is the strip map mode, and after that in the wide swath, which is called the scan SAR, which is having the 150 meter resolution. So we can see the satellites here, the how the ARS2 and the NVSat is looking. So initially most of the band utilization has been done with the help of the IIRS-1, IIRS-2 and NVSat satellites. So you can see this is the NVSat SAR image, which is showing the oil spill of the Spanish coast. So you can see in this image the dark signal, which is very much have the specular reflection due to the oil spill. And if the ocean any wind is blowing, then we can see the ocean will have the maybe have the small some higher backscatter due to the backscattering. So you can have the very much low backscatter in the background of high values of the ocean. So you can see how well we can distinguish the oil spill in the SAR image, and we can develop the algorithm also to detect the oil spill in the case of the SAR image automatically. So we can just do some algorithm, different algorithms are there to detect automatically and to estimate how much is the coverage of this oil spill, how much area it has covered. So that estimation can be done in case of the SAR images. Now after that we are having the radar set 1 and radar set 2 satellites, which is having the launched by the Canadian Space Agency in 1995 and 2007 respectively. So now radar set 1 is not operational, radar set 2 is still in the orbit, and it is having the different capabilities. So in the case of the radar set 1 we can see the polarization is HH only, and the resolution is varied from 8 meter to 100 meter, and it has the different modes like standard, fine, wide and SAR. So this nomenclature is like classical modes only, like we are having the strip map mode and the spotlight and the SAR. So accordingly the name is given standard, like strip map mode, like that. And talking about the radar set 2, it was launched in 2007 and it has the fully polarimetric capability. So it is a full pole SAR and the resolution is up to the 1 meter. So in the spotlight mode, and the swath width is around 20 to 500 kilometers. So different imaging modes, which is called the spotlight, strip map, SAR and wide it is, and it has the capability of both the right looking and left looking, means from the orbit it can look in the left direction also and the right direction also, and the geolocation accuracy is also very much higher in case of the radar set 2. So here you can see this is the radar set 2 image of the Dehradun area. So you can see this is the full polarimetric SAR image, where you can see the volume scattering as the green color. So all this vegetation and other thing you can see as a volume scattering, and this pink or red we can see like a double bound scattering. It is coming due to the like artificial objects, urban settlements, and that will give the double bound scattering. So not only the SAR image is a black and white image, so we can generate color out of it using the polarimetric or fully polarimetric SAR images. And here in case of this open lands and this one, it will reflect as a blue color, and it is actually giving the surface scattering. So depend on the scattering mechanism of the different targets, so we are having the different backscatter, and accordingly if we are having the different polarization, then we can distinguish different targets, and we can have the RGB composition, and we can do different polarimetric decompositions also. So we are having different polarimetric decomposition like poly decomposition, and we are having the Freeman decomposition, Yamaguchi decomposition. So depend on the different decomposition, we can detect a particular target with the fully polarimetric capability of the SAR sensor. So the radar set 2 have this capability of the full polarimetric SAR. Now recently the launch of the Sentinel 1A and 1B, which is mostly used by, because it is the free open source data. So it is launched on the Sentinel 1 is launched on the 2014, and Sentinel 1B was launched on 2016, and up to 2022 it has functional well. But after that it is not working, and actually one more satellite which is called Sentinel 1C has replaced with this year only the older satellite 1B, and now both Sentinel 1A and 1C are operational. So and the specification is actually it is a C-band satellite and with the single and dual pole. So by default it is acquiring the mostly the data in VV plus VH mode, dual polarimetric mode, and interferometric wide swath. So it has the different modes like IW, which is called the interferometric wide swath, EW, which is called the extra wide swath, SM is the strip map mode, and WV is called the wave mode. So mostly by default it will operate in the interferometric wide swath, which have the 5 into 20 meter resolution, means 5 meter in the range direction and 20 meter in the azimuth direction. It has the resolution, and it give different level of products, like it will give the SLC image also and ground range image also. and with the help of the one of the software, it is given like a snap software. So with the help of the snap software, we can just do the terrain correction and ellipsoid correction of this SLC and the ground range images to generate the images in the earth geometry, so that we can compare with the Google Earth or any other satellite products, or we can say other optical images or hyperspectral images. So these are the Sentinel 1A, 1B, and now the 1C also. So you can see this is the Mumbai area of India, and how the Sentinel-1 has acquired the data. So in this image you can see this is the Mumbai port is there, and in the right hand side you can see multiple ships also there. So in case of SAR, the ship detection is very much good application, and we can see how well we can distinguish the ships in the SAR image, because it has the very much darker background in the back, and the very much ship is it is an artificial object. So in this case of SAR, that type of metallic and the artificial object will have the very much higher backscatter, so it will be detected very easily in case of the SAR images and the ships. So in this image you can see at around 20 meter GSD, you can see how we can see different ships of different shapes, and how the urban settlements are having the different high backscatter. Now this is the Sentinel one is also giving the interferometric wide swath mode. So it have the pair of the two we have the pair of the images of the same area after the repeativity of 12 days. So with the after 12 days the sensor will look the same place, and using these two images we can do the across track interferometry to generate the either the digital elevation model, or we can generate the surface displacement map using the interferogram. So this is the recent Tibet earthquake we have can see. So this is the interferogram we have generated using the Sentinel-1 images. So you can see this is different fringes, and this different fringes are actually giving the idea of how much displacement has been happened. And as you can see in this interferogram, this each fringe will give the idea about how much displacement will be there. So we can count this these fringes, and if we multiply with the half of the wavelength of the SAR sensor, then it will roughly give the idea of how much is the displacement in a particular area has happened. So you can see very much higher complex in the middle of which is the center point of the earthquake, and how it is changing the interferogram pattern of the Sentinel-1 images. Now ISRO has the C-band satellite in the form of RESET-1 and 1A. So RESET-1 is the satellite which was launched on 2012, and it was decommissioned on 2017, and after that the follow-on mission was there, which is called the RESET-1A, or we can say it is a EOS-4 also. So EOS-4 is the Earth Observation Satellite and 4. So it was launched on February 14, 2022, and it is still operational. So normally in the RESET-1, it is a C-band satellite, and it is having the polarization like HH, VV, HV and VH. It have the different mode like FRS, MRS, CRS, and the resolution is varied from 30 to 50 meter, and the swath width is from 20 to 240 kilometer. So and this is the normal geometry of the RESET-1A. So you can see the different acquisition. So we can have the different modes, like we can have the spotlight mode also, we can have the strip map mode also, like this is a strip map mode, this is the spotlight mode, and this is the ScanSAR mode. So this different modes is explained in this figure. So here you can see the different RESET-1 imaging mode. So we can have the HRS, which is called the high resolution mode, which is the actually the spotlight mode, and we are having the FRS1, FRS2, MRS and CRS, and different resolution we can have from 1, 3, 9, 25 to 50 meter. So different modes will actually have different resolution. So if we are having the spotlight mode, then we are having the high resolution of 1 meter. FRS1 is the strip map mode, we are getting the 3 meter resolution. MRS and CRS are the scan SAR mode, and we are getting 25 and 50 meter resolution. So these are the reset 1A modes, and similarly we are having the reset 1A modes also, in which we are having the 50 meter for the CRS mode and 33 meter for the MRS, and 3 meter in the FRS mode, and 3 meter with the smaller swath width, which are having the FRS2 mode, and for the HRS, which is a high resolution spotlight mode, which is having the 1 meter resolution. And all this having the different polarization from single, dual to the full pole also. And the reset 1 and 1A have the one concept which is called the circular or hybrid polarimetry, which is actually the special type of polarimetry in which we can have only the dual pole capability, but the with the generation of the Stokes parameter we can convert to the full polarimetry also. So we are having only the dual pole, like we can receive like circular, and we can transmit as a circular and receive in both the things. So we are having either the RH or RV configuration, which is called the hybrid polarimetry configuration. So that thing actually help us to reduce the means the PRF capabilities and the volume size in case of the hybrid polarimetry. So we have the both the option like hybrid and the full pole in case of the EOS4 or reset 1A mission. So we can see this is the full scene of the FRS1 mode. So this is again the Dehradun area of the EOS4 image, and this is, you can see one building which is called the FRI, Forest Research Institute, in the Dehradun. So this is the 3 meter resolution. You can see the details in case of the SAR. So this is the building, and this is all the vegetation nearby, and small bright objects are all the small houses or any settlements in the SAR image. Now we have learned about the X band system and C band system. Now we are going to the S band system. So S band, we are having NOAA SAR S, which is called the small SAR satellite. It is actually the developed by the UK Space Agency. So it was launched by ISRO, and it has the collaboration with the ISRO also, and it is also giving the data sharing with ISRO, and we are getting the S-band SAR data. So it is a dual polarized, and it has a different imaging mode like strip map mode, scan SAR, and the maritime mode with a resolution of 60 to 30 meter. So you can see this is the NOAA SAR images. So you can see this is the normal ground range image of the NOAA SAR, and after doing the terrain correction, so this terrain correction has been done by us only. So this is we have generated the terrain corrected image of the NOAA SAR as image, so that it can project to the earth geometry. So different products can also be generated with the help of the SAR if you know the algorithms and physics behind it. So, and this is another image of the NOAA SAR of the Ahmedabad area. So you can see this is a 3 meter resolution, and you can see this is the Ahmedabad in the India, Gujarat area, and this is the lake actually. So this is giving as a specular reflection and appear as black in the SAR image, and this is called the Kankaria Lake in Ahmedabad. Now going towards the L-band SAR system. So we are having the first satellite, actually SAR satellite, is the CSAT. In all the frequencies, L-band is the first satellite which is launched as the CSAT in 1978. So it has the mission lifetime of 105, and it has the first mission in SAR mission, and it is in the L-band, and it has the single polarization with the resolution of 25 meter and the swath width of the 100 kilometer, and it is actually use the strip map mode in case of the imaging. Another L-band, it is actually the Japan Aerospace Exploration Agency, which is called the JAXA. It has the two satellite like LOS-1 and LOS-2. So it has the capability of the imaging modes of spotlight, strip map, and scan SAR. and having the resolution of 10 meter to 100 meter. So it is the ALOS 1 was launched on 2006, and the ALOS 2 was launched on the 2014, and ALOS 2 is a fully polarimetric SAR, so we can have a 1 meter resolution also in case of the spotlight mode. So you can see this is the ALOS 2 image of 0.6 meter Barcelona image. So you can see the details, how well we can see a particular target in case of SAR image. So this is the Barcelona image. Now another L-band sensor which is called the Japanese Earth Resources Satellite JERS 1, and it was launched on 1992, but actually the end of mission was up to the 1998 only. So it has the L-band, and it is also have the HH polarization only and the repeat cycle was of 44 days. Now upcoming mission is the L-band and S-band, means first mission which is having the multi-frequency in case of the space-borne mission for the Earth observation. So we are having this is the NASA and ISRO collaboration mission, in which the L-band is actually made by the NASA and the S-band is made by the ISRO. So it is actually have the resolution from 3 meter to 10 meter, and actually normally the SAR mode actually have the limitation of the resolution. So as I have said, the strip map mode have the resolution of L by 2, means if we are having the 12 meter antenna, so we can get a resolution of 6 meter. But if we want to increase the SWAT, then we have to compromise with the resolution, means if we want to have the SAR imaging, so we are having the multiple beams. So that multiple beams actually utilize the synthetic aperture time, which is used for the synthetic aperture creation. So that will reduce the synthetic aperture length and the resolution in the azimuth direction. So the SAR will increase the SWAT but reduce the resolution. But this problem is solved using the sweep SAR mode, which is having the high resolution and the high SWAT also. So you can see using this sweep SAR technology, in which the large reflector antenna is used to generate a larger SWAT in case of the NISAR mission, and we are not compromising with the azimuth resolution, and with the increased SWAT we are having the high resolution and in the both frequency L and S band. So this NISAR mission is scheduled on this end of the July from the ISRO only. So ISRO will launch this NISAR mission, and it has the open data policy. Once it is all the system parameters are corrected, it is open for all globally it is available for different applications. So main application is the it has the interferometric, it has the polarimetric. So different application related to the interferometric and polarimetric application can utilize this data. Now the P-band SAR system, we are having only one space-borne sensor, which is called the biomass satellite mission, and it is recently launched, which is on 29th April of 2025, and it has the resolution of around 200 meter spatial resolution, and it is mostly used for the to estimate the above ground biomass with high accuracy. So it is using the concept of Polin SAR, and backscatter analysis can be done to have the estimation of the biomass, and it is the fully polarimetric SAR with the frequency of 435 megahertz with a wavelength of 70 centimeter. So it is the first P-band mission in the space, and it is recently launched. So some first image is actually released of the Bolivian rainforest. So you can see this is the 200 meter resolution image of that biomass mission, in which is a fully polarimetric SAR. So we can generate the RGB image. So here you can see the different features, like we can see the water bodies, forests, wetlands and grasslands. So that water bodies you can see as a specular, it is becoming black. Green is all the vegetation, and the blue is the open field or grassland, which is giving the surface scattering type of thing. So this is the P-band biomass mission. So this is a summary of all the spaceborne SAR system. You can see from CSAT, SIR, IRS1, NVSAT, RadarSat 1, 2, RESAT 1A, JUS, ALOS, PALSAL, Sentinel, TerraSAR X, NOVASAR and NISAR. Now we can see some of the airborne SAR system also. So airborne is the mission like AirSAR, which is the NASA airborne system, which is having all these three multi-frequency. So in case of spaceborne, we have seen first the SAR mission which is going to be launched, which is multi-frequency. But in case of the ASR, we can deploy multi-frequency SAR also. So we can have the P band, L band and C band in the same airborne sensor, and it has the different resolutions also. So we can have the azimuth resolution of 1 and the slant range resolution of around 10 meter, or depend on the bandwidth. So we can have here the bandwidth of 20 and 40. So if we are using the 40 megahertz bandwidth, we can get a 5 meter, and if we are using the bandwidth of 20 megahertz, then we can get a resolution of 10 meter, because earlier I have told you the formula of C by 2B. So that is the way we can reduce the range resolution. So this is the ASR airborne ASR image of the San Francisco. So you can see it is a quad pole system. So we can generate the RGB image or the poly decomposition. This is a poly decomposition image only. So you can see how well you can see the vegetation, and this is the buildings, and this is due to the orientation of the structures with the flight line of the AirSAR. You can see it is appearing as a different backscatter and giving the volume scattering type of thing. So it is giving the double bounce, and due to the orientation it is giving the volume scattering type of thing. So here full blue is the ocean is there, and this is the vegetation. Another is the UAV SAR mission, which is called the uninhabited aerial vehicle synthetic aperture radar. It is having two types of SAR antennas. One is called the LNP, which is called the air moss, and another is called the Glisted, which is the car band. So this is actually the car band is still operational, and air moss is active in 2010, but the car band UAV mission is still operational. And you can see here it is the different purpose. You can see the car band is used for the interferometric SAR. So it is used for some deriving of the some surface displacement or the digital elevation creation. So that type of things we can do with the airborne interferometric system. So you can see this is the UAV SAR image of the Carmel Valley of the California. Another NASA airborne system is the GeoSAR, which is called the Geographic Synthetic Aperture Radar, which is having the P band and the X band, and it has the resolution of around 1 meter in the X band and the 3 meter in the P band, with a swath width of 10 to 12 kilometer. And it is different application like digital elevation mapping and the forest structure analysis. Another is the EcoSAR, is an advanced airborne polarimetric and interferometric P band. So it has both the capability of polarimetric and interferometric P band, and it is used or designed for the biomass estimation, and it is also the NASA airborne system, and different application like forest, carbon accounting, ecosystem health and climate we can use with this airborne system. Another airborne system which is called developed by the DLR Germany, which is called the ESAR, or we can say experimental SAR. So it has the all the bands X, C, L and P, and we can just visualize this image here how well we can the full polarimetric ESAR image in case of this and it has the resolution up to 1 meter and the swath width of 3 to 15 kilometer. It is a fully polarimetric and the INSAR capabilities also, and it was operational till 2010. Another is the JAXA mission PISAR. So PISAR is all developed by the JAXA, and it has the two band X and L band with the resolution of 1.5 meter, and it has the simultaneously dual band SAR. It is used for the urban monitoring and the soil moisture estimation. and one is called the Airborne Synthetic Aperture and Interferometric Radar Altimetry System developed by ISRO. So it is basically the altimeter mission which actually calculate the height of the terrain using the altimetry technique, using the range information, and it has the vertical resolution of 1 meter, and it has the basically it is the topographic mapping is the primary application for this ISRO mission. So this is a summary of all the airborne SAR systems like ASR, UAV SAR, PISAR, GeoSAR, EcoSAR and ESAR. So we can just quickly just see the different SAR and optical images here. So you can see this how we are having the SAR and optical images. So you can see this is the reset one US SAR image of FRI. You can see this is the SAR image and this is the optical image. So this is the optical image of the same area, and here you can see this is the you can see the FRS1 mode image of the Ahmedabad region. So you can see this is the bridge here in case of the SAR, how well you can distinguish the bridge here, and this is the optical bridge you can see, and this is some different structures in the SAR image, and you can see here the buildings are there which is giving the high backscatter here. So and different here the buildings, you can see the high backscatter here in the SAR image. And this is the reset 1A image of the Kolkata region. So you can see how this is the Howrah bridge actually. So you can see the optical image and the SAR image. So this is how the bridge look like in the optical image and in case of the SAR image, and how this high backscatter is due to this urban things here. So this all this high backscatter is given due to the urban settlements. So you can compare SAR and optical image, and this is the US image of the Mumbai area. So you can see different ships in 3-meter resolution. So you can see this is a 3-meter resolution ships, and you can see here you can see the details inside the bigger ships with a 3-meter resolution. So this is you can see how we can detect the ships in the SAR images. It is another image of 3-meter resolution. Here also you can see the bridge of the in the SAR image. It is a Kolkata region. Now you can see the US or reset one have the SAR interferometric as a capability as an experimental mode. So it is not dedicated to the SAR interferometry, but we have just analyzed the possibility can we do with the US4 SAR images. So we have acquired the master and slave image of Alwar region in the India. So we can see from that we have proved the concept of the SAR interferometry for the US4 emission also. So you can see this is the all mountain area, and this is the digital elevation model we have derived from the SAR interferometry technique. So these are some of the interferogram patterns we are done. So all this methodology we have developed here in the ISRO. And so you can see all this interferogram formations and the flattening, phase unwrapping, phase to height conversion and geocoding of them we have generated for the USR interferometry. So that's all in this lecture. So I have covered most of aspects of the spaceborne and airborne SAR systems. What are the different parameters in designing the systems? What are the critical parameters like wavelength, resolution, look angle, and the polarization for the spaceborne as well as the airborne systems, and how actually we are getting different products, and we are having the different images in case of the spaceborne and the airborne systems, and different application we can do with the optical and with the SAR images, and how we can compare that SAR images with the opticals. So SAR is always a complementary to the optical. So as a reference we have to take optical only, but for the interpretation of the SAR image initially. So because we are more familiar with the optical image, so first we have to, if we want to do the interpretation in the SAR image, so we can have one reference image optical, and with respect to that we can see what are the objects are actually higher backscatter or lower backscatter, and what are the different SAR sensors are available in the globally, so that you can utilize for your application what resolution you want, what polarization you want, which look angle you want, and what type of system is preferable for in ordering the data for your particular application. So thank you all for joining this session, and if you have any query, and then I will just answer after a few